Well, Professor Kosnukov, thank you very much for organizing this. And it's a great pleasure for me to speak to your members and colleagues about some of the work that we've been doing. And I'll try and be relevant to the objectives of the Theory of Plasticity department. Although some of the work that I will describe relates to elasticity, but I will also mention some aspects of applications in plasticity as well. So the work starts with this concept of poro-hyperelasticity. So you have a fluid saturated elastic material, but this is not the conventional elastic material. It can undergo large strains. Large strains means that it's like rubber-like materials which can stretch to 100% sometimes. And this has applications in what are called soft tissues. And the soft tissues are like brain material or arterial tissues. Now, all these materials have plasticity in there as well, but I think for the interests of the seminar, I'll focus attention on the elastic behavior of the material. Other materials are like geomaterials, earth materials, very coal beds, like coal mining, mine coal, used in methane extraction. The people who are interested in the Russian Academy of Sciences oil and gas exploration, the coal that's left behind is a good location for putting greenhouse gases. So climate change problems can also be addressed. So the hyperelastic medium that I'm looking at has a structure in it. It has some solid material in there, some porous materials as well, and there's also fluids in the pore space. So this is a complicated material, but the work started off in the 1940s, even earlier than that. Verigin from Russia and all the other people, Zaryetsky, they've also looked at soil mechanics problems where they large strains are important due to plasticity as well as creep. So the type of work that I'm going to describe is very simple in the sense that it's got hyperelasticity in there, this large strain elastic behavior, stretching out the material, and fluids are in there. So they interact between them, and that makes the study very interesting. So a particular kind of application is related to head injury. Say, for example, there's an impact during head injuries, and the head injury doesn't materialize immediately, but you get things like extradural hematoma. That means the blood accumulates in there. It presses on the brain tissue, and the depletion of when the brain tissue gets compressed, it will have the effect of removing the blood from the brain tissue. And that's a very serious problem. My brother, who is a neurosurgeon, is involved in this kind of activity and initial management of head injuries. So this is really the trauma that accompanies. So you need to be able to not suddenly release the pressure, but gradually release the pressure. And that requires some assessment of how fast can you relieve the pressure so that the edema doesn't set in and it doesn't affect the brain. So this is one application. The problem was recognized in the 1800s, in the middle of the 19th century, by the Scottish surgeon who was doing brain surgery, and they didn't have access to CT scans and other things. So what they had to do was basically dissect the brain of a corpse or cadaver, for example. And this is the modern imaging techniques that are MRI, for example. And these images are available in the museum in Glasgow in Scotland, for example. So they have, each plate has a section in there, and then it's interesting to note that people did look at the brain as a tissue that is composed of several layers as well. So going to the multiphasic part of the behavior of this fluid saturated elastic medium, the important thing to note is really that you do get, there's a fluid pressure developing in the pore space. The solid material, the porous tissue, also takes some stress. So the externally applied stresses is partitioned into these two. So this is really a fundamental concept in multiphasic materials. Just to stop for a moment, I'll send a copy of this entire presentation to Professor Kostnikov, so he can give it to anyone who is interested in the material as well. So this is really the fundamental concept in multiphasic material, that the external stresses that are applied is partitioned between the phases that compose the multiphasic material. So in the case of a fluid saturated porous medium, it has the skeletal material and the pore fluid in the pores as well. So I've taken Cauchy's stress as the discussion part of it, but it could be any other stress measure as well. So this is a constitutive relationship, the partitioning, and it's based on observations as well. So the fluid is supposed to be in the accessible pore space. Sometimes the fluid is in inaccessible pore space, but we are looking at the fluids that can flow. So what happens to the fluids that's inaccessible, say like in a closed void, then there will be diffusive processes that take place within the brain. So the pressure differences can result in pressure migration through the brain tissue as well. So if you look at a representative volume element, which any multiphasic medium must consider this concept, and that is the fluid is in there. The fluid can be within the so-called mesoscale, that is Stokesian fluid. It's like a Stokes' flow, for example. So you can get viscous fluids. The fluid can be very complicated because it's blood. For example, in the brain tissue, it can be blood, and blood is corpuscular. That means it has particulates in there as well. So the fluid can have very complex relationships as well. So the brain tissue is complicated, the fluid itself is complicated. So inside the brain tissue, you can have fluid inclusion, so you can have Fickian diffusion. So the problem becomes very complicated. Now you can introduce things like electrically active fluids into the region there, and that makes it much more complicated. So one has to decide where you want to stop the actual partitioning or upscaling of the process is very important. So the scaling of the process, which can result by considering very different scales of mechanical, molecular, electrical behavior. So the problem can get very complicated if you want to make it. But at the end of the day, you need to be able to solve some simple problems which will illustrate what is observed macroscopically, in other words, in this level. This influence, the influences of these scales are important, but I think for the sake of solving a reasonable problem, we look at it from this continuum scale. So in the continuum scale, what we have is really fluid pressure inside the porous medium. Then it can vary in space, and the variations in space can give rise to hydraulic gradients, which can make the fluid flow. So improvements to the basic modeling was proposed by Maurice Biot. He was the Belgian scientist, and also other people as well. And what Biot's proposal tells us is really that the partitioning is now modified by this parameter. And this is called Biot's parameter, which tells the skeletal bulk modulus to the bulk modulus of the solid materials that composes the skeleton. So luckily for our purposes, this solid material that composes the skeleton is much more rigid than the skeleton itself, which means that your parameter, partitioning parameter, is given as unity, which is a useful simplification. There are other procedures that are used for partitioning as well, but I don't need to go through the details of this. Okay, so we assume that the porous material, the bulk modulus of the skeletal material is much greater than the bulk modulus of the porous medium, and it's much greater than the bulk modulus of the fluid itself. So if you make this assumption, then you can resort to the very basic assumption that there is a fluid pressure in the porous space, and then there's skeletal stresses, and that is sufficient to deal with the problem. So you can divide the skeletal stresses into the deviatoric part, which is this Sij dash, and the isotropic part, P dash, and not to be confused with the pore fluid there. So this is really the deviate isotropic part of the skeletal stress tensor, and this is the deviatoric part of the stress tensor. So these are two simplifications that we will use because it's much easier to work with in formulating problems. So now we have to look at this large strain behavior of the medium. And the large strain behavior, it follows a very standard procedure. It's got a skeleton which has a deformation gradient tensor. So this is the current position of a particle, and this is the original position of the particle. And the left Cauchy-Green strain tensor is really the F multiplied by the F transpose, which is really conventional continuum mechanics. And the F bar is, of course, this Jacobian there of the deformation gradient tensor multiplied by the deformation gradient tensor itself. The strain energy function, we are dealing with elastic skeletal material. So you need to have some sort of a hyperelastic material behavior, and the hyperelastic material behavior is characterized by these stress invariants. So your strain energy function now is dependent on the first invariant of this deformation left Cauchy-Green strain tensor, second invariant, and then the third invariant as well. So this is really conventional continuum mechanics, and the conventional continuum mechanics means that I can get the deviatoric part of the effective stress given by this expression. This is again standard continuum mechanics. And isotropic part, so it's really the derivative of the strain energy function with respect to the two invariants of the left Cauchy-Green strain tensor. So an example of the strain energy function, there are so many strain energy functions that are possible, but for the purposes of applying it to biological materials, we use this so-called reduced order polynomial, second order, And as you can see, that there is one term which is really the so-called neo-Hookean material. If the exponent is equal to unity, apologies for this, this should be I2 there. So this gives me the Mooney-Rivlin type strain energy function, and so on and so forth. So there are as many strain energy functions. So it's a matter of selecting the one that's most applicable to the situation that you are dealing with. So you can recognize the constants there in terms of the shear modulus there, and then the inverse of that, the 1 over the T1 corresponds to the inverse of the bulk modulus, for example. So these are connections that you can make with respect to the choice of the strain energy function. So the neo-Hookean form is really that C20 is equal to 0, and then D2 is equal tends to infinity. And then I can express the strain energy function in terms of the stretches in this particular way. So this is again a standard reduction in continuum mechanics. Now, the important thing to note is really that the poro-hyperelastic skeleton material is assumed to be isotropic. So that means it has no directional properties, but you have to be careful. Sometimes when you stretch, when you give the material large stretches, the molecules can align. So that can introduce anisotropy into the discussion. So we don't need to deal with it right now, but I think it's possible to address this issue as well if you want to make it more complicated. But that could be best done by using computational approaches based on finite element technique. And involved material was isotropic, but by stretching it, I made it anisotropic. So this is really something that needs to be considered. But I think for our purposes, for this elementary treatment, we'll just consider it to be isotropic throughout the deformation. What about the flow through the porous skeleton? We have flow through the porous skeleton. We have mass conservation principle is this. Here's the velocity of the fluids, velocity of the solids. So when you have large deformations, the fluid moves, the solid moves. It's the relative velocity that needs to be considered in the mass conservation equation. And that gives us this relationship. And the fluid saturated hyperelastic material is assumed to be subjected to external pressures, external loads, excuse me. And the pressures can develop, and this can contribute to a gradient in the so-called reduced Bernoulli potential, which causes the flow. Now, this is not the only way. I'm going at basically using Darcy flows to look at the process of fluid flow, but it doesn't have to be. I can have Richards flows, Brinkman's flows, Bingham discussions with regard to the modeling. So all these are possible, but I will restrict attention to only Darcy flow. So if it is Darcy flow, then the right-hand side of the, excuse me, I'll go back again. This one comes out to be exactly characteristic. And again, I reiterate that I can also make the fluid flow directional dependent by stretching it. So if you give the large strains to the material, then there can be pore adjustment. So the pores will align themselves to give favorable fluid flow in one direction compared to the other. It can have plasticity effects, which are also anisotropic. So that's an entirely different discussion. And I'm sure that's important to the Institute specializing in plasticity aspects as well. So permeability, this scalar property here can also attain anisotropic characteristics as well. So these are things that can be incorporated, but you do this with a lot of work, you know, and at the end of the day, you have to make sure that the work is manageable in terms of getting some results. So first thing to do in situations like this is really to look at the one-dimensional poro-hyperelasticity problem. So that means this is the classical one. Everybody has to deal with the one-dimensional one. And if you can solve the one-dimensional problem, then you can understand how the physics of the problem is with regard, mathematics and physics of the problem. Now this problem was examined, the one-dimensional one, was examined in the mid-1960s by my research supervisor, Professor Gibson, who passed away some years back. And he looked at it in terms of consolidation of settlements. And Gibson's formulation incorporates linear elastic behavior. So that means the hyperelasticity is not there. So it's an incomplete formulation of the problem. And the problem results in a nonlinear partial differential equation for this so-called porosity of the medium or void fraction. And that is an important benchmark that one can use to test any further developments to the theory as well. That's Professor Gibson, who passed away in 2008. And I think, you know, he made a lot of contributions to geomechanics in particular and applied mathematics as well. So here's the problem with dealing with the one-dimensional. So first of all, I have a medium, which is a column of the material, which is constrained in the two directions there. It's supported on the base. Stress is applied to the upper surface there, and you allow the fluid to escape. So you maintain the fluid pressure at the outer boundary to be 0 at all times. So this is the classical one-dimensional problem. So this is a constrained, this is a poro-hyperelastic material, which is subject to a stress. So this sigma naught could be a Heaviside step function of the stress, and it's applied and kept constant, and the medium is allowed to compress with time. So time is really an important consideration, because the fluid will take, if it is just if it is hyperelastic, the compression will take place immediately. But if it is poro-hyperelastic, the fluid has to escape, and that escape of the fluid takes time, and that will result in the compression also taking place with time. So I can formulate the problem in the conventional way. Here's the deformation. The two constrained sides gives me these values of the displacements. So the deformation gradient tensor is this, and the left Cauchy-Green strain tensor is this. There's only one stress that we are interested in, and that's the axial effective stress, which is this. So without going through the details of the derivation, I can say that the deformation now is the original position plus the displacement as well. So the effective axial stress is now this value, and there's only a single equation of equilibrium, which involves the total stress with respect to x, and that involves the effective stress and the pore fluid pressure as well. And if I substitute the expression for the stress in the single equation of equilibrium, I get a very complicated nonlinear partial differential equation for the displacement there. So this is really where it looks like a nice complicated equation, but you know, what can you do with this is really the basic question. So getting a solution to this nonlinear partial differential equation, we tried several things. My collaborator, Alexei Zuvarov, and I spent months trying to figure out, is there a Mathematica type solution or Maple solution that might give nonlinear solution to this nonlinear equation, nonlinear partial differential equation? because there's time variable there and the space variables there as well. So the answer is really, I don't think there is. I mean, if there is one, it would be so nice. I'll be very happy if somebody can find one. But I think, you know, the chances of getting them are very, very slim indeed. So this is a simple initial boundary value problem, but getting a solution is not very easy. So, but we can look at the limiting cases. So that means when the deformation gradients are small, then this du over dx will be very much less than unity. And then the square of the gradients can be neglected. And then the previous nonlinear partial differential equation reduced to exactly what Bio had for the one-dimensional consolidation test for soils, for example. So here's the stress that's applied as a Heaviside step function. The initial conditions are classical in the sense that I've assumed that the displacements are zero everywhere at time t equals 0. And that gives us a nonlinear partial differential equation. I can decouple the pressures, and then that gives me another nonlinear partial differential equation for the pressure variable. Again, they are complicated functions, and the chances of getting a solution are extremely, virtually impossible to get a solution in an exact closed form or in some form. There are techniques that you can apply in terms of the nonlinear initial boundary value problem. We can solve it using perturbation schemes. You can use variational methods to solve it, finite difference schemes, so finite element schemes, Galerkin techniques, all the other computation schemes can be used. But I think the finite difference technique is the most straightforward because you can use the finite difference to both spatially discretize the region and temporally discretize the region as well. So the temporal discretization uses the conventional Crank-Nicholson technique, but there are other 3-point options as well, which is possible to use. But I think, you know, this system works. So the finite difference scheme is the best one to use. The only problem is really that when you deal with problems like this, you cannot get general results. So every time you change, for example, the strain energy function, I had to do the calculations over again. So there are lots of calculations that needs to be done, but this is the price you have to pay if you want to formulate the problem correctly. So we use the one-dimensional case. So these are the strain energy functions. The parameters that I use, I can obtain it from the literature. Permeability values are there, the viscosity is known, the column is the fluid pressure is allowed to diffuse to 0 at the surface there. I apply a stress there. This is just as a calculation exercise rather than as a potential application for any realistic situation, but it shows that the method works. So we get the numerical results using this finite difference scheme. We use a reduced polynomial for the strain energy function and consider the results for the neo-Hookean case. So that means some of the constants are set to 0. So that's one solution. The second solution is the bioconsolidation problem that Gibson solved. But that's for infinitesimal strains. So here's where the problem is, that you do the large strain consolidation, but utilize only linear elastic constitutive relationships. So there's some inconsistency, but it's useful to see what the results give. The third possibility is really to look at all 3 problems and use fairly robust computational code, which is Abacus, and that allows us to solve the problem using the computation scheme, which everybody seems to be familiar these days. So here are the results for the one-dimensional consolidation displacement. So the displacement of this is the displacement of the upper surface. Negative means that it's going in the negative direction of the z. So this is the reduced polynomial solution using the finite difference schemes. The solid lines are finite difference schemes, and the dots are the finite element solutions. So you can see that the expressions give exactly the same as the finite element scheme as well, and they match exactly. The second one is the Neo-Hookean one. Again, the results for the finite difference scheme match the computational finite element scheme as well. And the linear elastic case, as obtained by Gibson, gives us the same results, and we can implement the linear elastic case in the finite element scheme as well. So the important thing to notice is really that all three give different consolidation settlements there. So in other words, the reduced polynomial gives me a lower consolidation settlement, and then the linear elastic one gives me a higher consolidation settlement. The rates at which the consolidation takes place, there is some differences, but not much. And the computational scheme matches exactly the finite difference scheme, which is a mathematically rigorous one as well. So it means that we have identified that the finite element scheme is possibly a good way of dealing complicated geometries as well. This is a very simple one, and the complicated geometries can arise if you want to say, for example, model the entire brain, the two lobes of the brain, and then apply pressures onto one location, etc. So make the problem a lot more complicated in terms of the geometry, then the mathematical solution is impossible. So that means you have to resort to some computational scheme. So this is really a very good test standard. So this paper was published in the Journal of Mechanics and Physics of Solids, along with two other papers as well. But I think, you know, it means that there's a benchmark now that anybody else who develops any other technique can at least see whether these solutions give, that their solution is comparable. You try it out with the benchmark solution first. So the one-dimensional the time-dependent behavior of the fluid pressure, again, so you can see that it starts off with exactly what you applied in the at the top there, and then it diffuses very quickly to zero. The time it takes will change depending on the model that you're using. The reduced polynomial consolidates much faster than the Neo-Hookean one and much faster than the linear elastic one. So there are again, the finite difference solution is a solid line, finite element are the dots, and they come out pretty close to each other within sort of numerical accuracies. So the other problem is, as soon as you solve the one-dimensional column problem, the next thing is really one-dimensional consolidation due to in a sphere. Before I go to this particular problem, I want to go back to the I would really like to get someone to, so you can do poro-hyper plasticity as well. In other words, instead of looking at elastic deformations on the skeleton, you can also consider plastic deformations as well. So all these problems that I will discuss is really ready for applications in plasticity as well. So in the case of the Department of Plasticity at Lomonosov, Moscow State University, this is something that you should get interested in, so that you can get students to work on this, and I'll be extremely happy to give them advice as well. So here we are. The second problem is again a one-dimensional case. The one-dimensional case of a poro-hyperelastic sphere, So it's a sphere which is now subjected to external compression, and the fluid pressure is allowed to dissipate at the surface. You maintain the fluid pressure at the surface to be zero at the boundary of it. So this is a classical case of the so-called poro-hyperelastic sphere. It was solved by Cryer in the 1960s, published in the Quarterly Journal of Applied Mechanics and Applied Mathematics. Gibson and his colleagues revisited this problem in 1963, and they also did the elastic experiments as well. And the poro-hyperelasticity problem was examined by myself and Alexei Suvorov, and it's examined by, the poro-elastoplasticity problem. So no hyperelasticity there, but elastoplastic there. So that means there's a yield function there, as well as fluid migration in the system. The only problem is really that when plasticity develops in a material, you change its stiffness, and you also change its fluid transport characteristics. So in other words, where material has yielded, you can get different fluid flow characteristics. So it's important to extend this work. Here we did the very elementary one where the material properties were elastoplastic, but the fluid transport properties remained the same. You can extend it to other situations as well. So this problem has been looked at in terms of the conventional small strain elasticity and small strain elastoplasticity. Here we want to go into large strain fluid flow as well. So the formulation of the problem is exactly the same as what we did for the one-dimensional column. You have basically the deformation gradient, then the left Cauchy-Green strain tensor is this. There's only one spatial variable, which is really, for mathematicians, this is really wonderful. You know, you have only one spatial variable to worry about. And then the stresses are, there are two stresses now, the radial stress, and then there's also the hoop stress as well. So the equation of equilibrium now comes out to be this. So you have the effective values of the radial stress and the circumferential stress as well. And you get the single equation of equilibrium for the displacement and the pore fluid pressure there. And I can use a representation, which means that I can say that the current coordinates will be the undeformed coordinates plus the displacement, and Darcy law and spherical symmetry gives us this result. Again, the problem becomes very complicated in terms of the mathematics behind it, but the mathematics is correct, you know, in the sense that there is nothing we can do beyond this. You can get the single differential equation for the displacement there. So this is the displacement, but whether you can do anything with it beyond that is extremely difficult. And the pore fluid pressures can also be obtained in exactly the same way. So we can go through the same motions as we did for the one-dimensional column experiment, and that gives us this result. So you can test whether the theory works by looking at the reduction to small deformations, and that gives us exactly Bio's result. And the boundary conditions for the sphere are that the effective stresses are this radial stress that's applied as a Heaviside step function. And the initial condition is really that everything is non-deforming and pressures are zero as well. So I can go through a calculation for the spherical symmetric. You have a strain energy function like this. And again, I have a linear make comparisons between the computational solutions obtained by Abacus code then the linear poroelasticity formulation, Neo-Hookean case, and the linear constitutive relationship, that means small strain Hookean elasticity, tackled by Gibson and them. So here are the results. The solution by Gibson is given by this value. Linear elastic small strain assumption is this, and the Neo-Hookean one is this. So this is large strain, linear elastic, and Gibson's small strain elasticity behavior as well. So you can, the only nice thing is really that all these three models can be implemented in Abacus, which tells that it's a good platform to use for comparisons as well. The other interesting thing is really that the pore fluid pressure at the center of the sphere, this is an important, this is the so-called Mendel-Krey effect. So physically what happens is really that the sphere compresses at the boundary, the fluid escapes, so that means the pore fluid pressure is zero, so all the stresses that I applied is transmitted to the skeleton. And that means the skeleton basically shrinks. And when it shrinks, it exerts an additional pressure at the center of the sphere. And this is the so-called Mendel-Krey effect, which was observed by Krey as well as Jean Mendel in France. And this is a load shedding from the pore fluid to the porous skeleton. And what it does is really that you get a pressure in the center, which is greater than what you applied at the boundary, which sounds very not physically, it's difficult to visualize, but it does happen. Actually, people have actually measured this. They have put in pressure transducers inside the sphere and then compressed it, and then you get the pressures rising up. Nowadays, you can get transducers where there are no leads there. You just put the transducer in the middle, and it can transmit the pore fluid pressures to the exterior. Okay, so there's absolutely no possibility of leakage occurring from the center to the exterior. So yes, you can see that the pressures do go up, and then the pressures reduce to zero as time progresses. So the finite element solution using Abacus comes out to be an exact match with the theoretical results obtained by finite difference scheme as well. The third problem is really, again, a one-dimensional, spatially one-dimensional problem. And you can go through this formulation of the problem by, this is really in the undeformed configuration, this is the annulus. So this is like an artery, for example. And then you have a pressure that's applied. And this boundary condition here, the Neumann boundary condition tells us that you can't get leakage from the inside to the outside during pressurization because there's no hemorrhaging from the artery itself. So this is really, again, a one-dimensional problem that can be solved. I won't go into the details of this, but I think it's important to, so that you get the conventional coupled nonlinear partial differential equations for the radial stretch and the pore fluid pressure. The boundary conditions are these. And you can solve this using the MATLAB program, boundary value problems and the boundary value problem solver, and the Abacus code as well. The finite difference code that we use is basically the MATLAB one that's available. So the reduction to the linear cases, again, this is really, I won't bother to go into the details of this, but the important thing is really that you can get instabilities occurring. So in other words, so you can get stretching for the same pressure. So that means there's a blow a balloon, right? when you blow a balloon, it takes a little pressure to get it started, but once you get a certain pressure, it'll start growing. Okay, so this is really like a ballooning effect, and people are concerned about this because in blood vessels, for example, you can get aneurysms developing. Aneurysm is an instability in the blood vessel, and that is and finding out at what pressures this can happen is important. So you can see the finite element technique solutions are very close to the computational solutions using MATLAB as well. Just to give a biomedical application, this is really an abdominal aortic aneurysm. So the aneurysm develops there, and that's something that people are concerned about. And the aneurysms can be fatal in the sense that if you don't catch it correctly, this can result in bursting of the vessels, and that is definitely something that you had to be concerned about. So we can apply the people who are vascular surgeons tend to use these stents to keep the instability under control, and so this is one typical stent as well. So we can apply the theory of the pressurization of the of an annular region. So if you apply it to the neo-Hookean case, only C10 is needed. So if you take a healthy adult aorta, and the values are, the radii are 10 millimeters, and inside diameter is 8 millimeters, exterior diameter is 10 millimeters and 1 centimeter, for example. And the value of C10 is about 200 kilopascals. And the average blood pressure of the healthy adult is about 120/80, or millimeters of mercury, or about 16 kPa. From the analytical results, that the critical pressure is 72 kPa. So that means you're well below the limit for creating an aneurysm or instability in the system. So you can do this for the other unhealthy aorta. The B is about 40 millimeters, A is about 38 millimeters. And you can go through the blood pressure is about 150/80 and or 20 kPa. So this the instability pressure is about 20 kPa, and the average blood pressure is also 20 kPa. So this is really one can use the information to make some diagnosis as to where you are in relation to the possibility of creating an instability in the tissue, for example. So I won't go into the details of this in view of the time. So what I'll skip this part and basically go on to yeah, I think probably in the interest of time, I'll skip this one as well. It's a good problem on shear in there. So to conclude, the concluding remarks on poro-hyperelasticity, it's an elementary treatment of the mechanics of a fluid-saturated material. It does not take into account evolutionary aspects. In other words, how does the anisotropy and other things evolve? And the test procedures, if such extensions are to be included, then you need to develop test procedures for parameter identification. And that's a real big problem, that there aren't many people who are working in this area in the experimental sense to provide all the information on how to develop extensions to this sort of elementary. I consider my treatments as my solutions as elementary treatments. So there are lots of other things that could be done to improve the modeling. robust computational platforms. So you need to be able to get the temperature in there as well. We haven't looked at thermal effects there. We have looked at the fluid part, hydraulic and mechanical. Of course, the living tissues are chemically active as well, and they are also electrically active. So if you want to look at the problem in a holistic sense, you have to consider lots of coupling effects there. So if you go beyond the hydraulic and the mechanical part, or the fluid and the mechanical part, then you get a full matrix developing of couplings. And that really does cause problems, because I think, if you develop a theory where there are no procedures for getting the coupling terms correctly studied, then you do, your developments have limitations there. So the work that we've done is published in in these journals there, and we have a couple of other papers in progress as well, the torsion problem, and as well as the pre-stress loss that can materialize in arterial stents, for example, due to poroelastic effects as well. Now, I think for the Department of Plasticity, I should at least talk about some plasticity effects there. So thermoporoelastoplasticity is one. So we looked at temperature, hydraulic, elastic, and plastic effects in materials. Not for not for applications to biological tissues, but certainly to geomaterials, for example. One of my other interests is really nuclear waste disposal, and the nuclear waste disposal effects require that you take into account heat transfer in the medium, fluid transport in the pore space, mechanical deformations of the porous fabrics, albeit small types as well, and some chemical transport is also important. So these are things that I think one can study, but I will exclude the chemical transport for the time being, just to give a brief illustration of what the hydromechanical modeling is. We've gone through the hydromechanical part of it in slightly in relation to the hyperelasticity one, but I think people have looked at it from continuum theory of poroelasticity as well. And the dependent variables are now the displacements, the temperatures, and the fluid pressures. So I have a porous material which has fluids in it, and it's subjected to external stresses. The skeletal part will also take some stresses, and the fluid pressures will also develop. You can look at double porosity media as well, but I think, in the interest of time, I won't go into the details on this. So the governing equations are basically the deformations of the skeleton are governed by the Duhamel-Neumann biotype. So here's the pore fluid effect there, thermal effects there, and then the classical Hookean elasticity coming in there as well. Darcy flow, and then I take a reduced model of Fourier heat conduction type. So there's some influence, there's no influence of the stresses on the heat conduction process, but there could be fluid flow in the heat conduction process. So your governing partial differential equations for small strains come out to be something like this. I have the displacement Navier equations, but I now have a pressure term in there and the temperature term in there as well. And the pressure is again controlled by the temperature as well, and the deformations, but the heat conduction is just a simple Fourier model. If you make the natural tendency is really to take these constants and then say they are dependent on the independent variables as well, which will make the problem very highly nonlinear. That means you don't know whether you even have a solution, or existence of the solution is not addressed. So computational codes, we can use material plasticity and damage in there, permeability, but it's a matter of selecting the right type of computational modeling applicable to the material that you are investigating. So we've done the modeling using the so-called COMSOL code, which is also a multiphysics code that's been looked at by many researchers. We were asked the question by my research sponsors, can we use this code and directly apply it? I said, no, you can't do that. You have to validate the code and then see if they are giving the right results for known problems. And that's something that I tell my students as well. You don't use your code and then give me a result. I want you to prove that the code works and that you have tested the code on known solutions for even simple problems. So the research sponsors were aware of this, because I said, if you don't do this, somebody from the regulatory agency will ask you the question, did you test the code? And if you say, no, we haven't, then of course, all the effort will be wasted. So it's important to tell the students who are going out to industry that first thing they have to do is make sure that they are comfortable with the code in terms of giving accurate, unconditionally accurate results. So the thermoporoelastic case we've looked at. Thermoelastoplastic case, we looked at the heated sphere problem. So in other words, what you have is a fluid-filled spherical fluid-filled medium in there. It has a spherical cavity in the middle there, which is filled with a fluid. Fluid-saturated poroelastic sphere. I can put poroelastoplasticity as well. And time-dependent variations in the surface temperature. Okay, so if I subject the surface to a temperature, time varying, and then you can see that as the boundary is heated, the pressures rise inside the cavity, and then at the temperature is switched off, the pressures take a little bit of time to decay, and this procedure can keep on going. So time-dependent variations in the cavity pressures, again, so you can see that they follow the poroelastic case quite closely. But the question is, can we do this for the elastoplasticity as well? So it's isotropic linear elastic behavior. So we use the so-called, not a von Mises plasticity. You can do this with von Mises plasticity or Tresca or Drucker-Prager or something with a hardening rule as well. So it's possible to use different types of plasticity, but we were looking at possibly clay-like materials, and this so-called CAM-clay plasticity model with isotropic hardening is used there. And the thermal and fluid transmissibility properties are uninfluenced by the yield. I made this remark previously in connection with the stretching of the hyperelastic one. So the same thing is applied here, that I will keep the transport processes invariant of the plasticity of the medium as well. So it's a form of weak coupling between the thermal phenomena. So that means there's no heat transfer is not influenced by the stresses, and it's not influenced by the rate of deformation of the pore fluid pressures as well. So your yield criterion is something like this. These are basically the isotropic stress and the von Mises stress is there as well. The yield surface is basically governed by this dotted line and this surface. So it can keep moving. The isotropic hardening can make the surface move, and that's also taken into consideration. So in the hardening rule, you have hardening parameter. There's a plastic volumetric strain which goes into the hardening rule there. And then there's also compaction regime as well. So if there's lowering of the stresses, that can also cause yield surface to either expand or contract. So these things are readily available. and you can use an associated flow rule for this particular material. Associated flow rule seems to work quite well. There are clays and soft materials like that. You can get associated flow rule, which you don't need to have a non-associated flow rule, which will have a different flow function in there. So consider the initial boundary value problem, which is a saturated sphere. Initial conditions are these, and the surface is subjected to temperature rise there, and the pressure is kept at 0 there. And the effective stresses are 0 as well on the surface there. So we want to look at how the pressures develop inside the medium there. And I give some values for the properties there. I think, this is available in the literature as well. So you can see the boundary temperature is subject to this Heaviside step function. The analytical solution is given by the solid line, and the COMSOL code gives us this result for the pressure developed at the center there. So this is really very simple poroelasticity type solution there. And now we compare the results between the elastic sphere and the elastoplastic sphere. So you can see the surface displacements are slightly larger on the elastic plastic case, where the plastic deformations take place, and the elastic deformations are slightly lower than that of the elastoplastic sphere. In terms of the pore fluid pressures that are developed, so you can see the results for the elastoplastic sphere is this. There's no analytical solution for that, but the computational solution matches very closely the ones that you get from the elastoplastic sphere there. And the elastoplastic sphere, the elastic sphere solution is this. They are pretty similar in terms of the response as well. So you can see that when you heat the material up, you can go on a certain path, and then when you cool it, it can go down a different path as well. So this evolution of the yield surface is an important, it's like thermoplasticity in conventional thermoplasticity situations as well. So the elastic, so just to give a COMSOL solution, abacus, analytical solution, we have only for the elastic sphere. So you can see the elastic sphere has this response. The COMSOL solution for the elastoplastic sphere and the Cantlay model at different values of the confining stresses will give rise to different values of the different responses there. So the objective of this analysis is really that you can't do analytical solutions for this. It's extremely difficult. You could, I suppose, but it takes a lot of time and effort to do this. But if you can compare the analytical solution with the COMSOL solution for the linear elastic case, then at least you have some legitimacy to apply it to the elastoplastic case as well. Some word of warning there. Sometimes your solution can become unstable there. So these are the COMSOL solution in blue there, and that can become unstable at short time intervals as well. And this is really depends on the time integration scheme that's embedded in the COMSOL solution, and that's something that one has to watch out for. You can improve this thing, but COMSOL, the time integration scheme is fixed. So, but luckily, at large times, the solution is very stable and gives very close correlation to the solution obtained using abacus. So here we have two intercode calibration. So in other words, I have used the COMSOL solution, which is a multiphysics course that actually solves the partial differential equations. and the abacus codes, which uses the Galerkin technique to solve the partial differential equations as well. And then there's an analytical solution for a very simplified case as well. So you can see, you can get solutions for the various responses, and then it showed that the abacus solution and the COMSOL solution come out reasonably close, which pleased the research sponsors. That means that they could solve all the practical problems using computational techniques. So the mathematicians might be left out now because of the ability for the computational techniques to do quite well. So concluding remarks, the development of analytical solutions in thermal elasticity become feasible only in highly simplified geometries involving one-dimensional cases. The one-dimensional compression of regions have been examined in the literature. Professor Pariso from University of Utah did this as well, and Alex Soroff and I did in 2012 and 14. There's a publication as well. These solutions are used to calibrate the computational codes, and that's very important. I think, you know, this is something that sometimes it's a symbiosis between the two. Sometimes analytical solutions can also contain errors. And this is something that we found out by comparing the solutions with computational codes. So we should not dismiss the computational codes as being sometimes like an outlier. They can help each other. The computational codes can help detect things that are wrong in the analytical approaches and vice versa. So this is something that is very important to note. So influence of various constitutive assumptions are examined through canonical problems. So I think I'll take this opportunity to formally thank my research group. This is Alexei Suvorov, and who is in Moscow there. I hope he was able to participate in the Skype meeting, but if not, I'll send him a copy of the presentation as well. This is my research group, whom I cannot see them because they are all quarantined because of COVID-19. And I'd like to pay a tribute to people who got me started in continuum mechanics and mainly hyperelasticity. Professor Rivlin, whom you have heard of, you know, he's a key person in the development of hyperelasticity. I had the opportunity to meet him in Reykjavik in 1975 when I was a very young graduate student and finishing my PhD, and so he left an indelible mark in terms of his contributions to continuum mechanics. And the second person is my research supervisor, Professor Spencer, who also passed away in 2008, and he did a lot of work on invariant theory, finite elasticity, fiber reinforced materials, plasticity of fiber reinforced materials, etc. So it's a good opportunity for me to pay my respects to people who really developed the subject. And he had a lot of connections with Viktor Nikolaevsky as well on granular materials, you know, so this is the effort continues. Okay, so I think I will stop there now, and I'll be happy to answer any questions anybody has. Anyway, so
yes, please, questions.
Yeah.
So, okay, may I ask a question?
Please, yeah.
Okay, thank you. So, yeah, I would like to say it was a quite interesting presentation, and it was interesting for me and for my colleague because we work in the same area, about the same area.
Wonderful.
And so maybe that's why I have some questions. For example, it was quite surprising that there is a big difference between solutions if you consider different hyperelastic models. So
Yes, yeah.
I couldn't catch your explanation for that. Maybe you repeat it again.
I think this differences between solutions when you incorporate hyperelasticity is fairly well known in the sense that you do get discrepancies because of the Cauchy strain that, left Cauchy grain strain tends to incorporate additional terms in there. And that this discrepancy has been observed in other finite strain solutions as well. And exactly what is causing it, I think you need to, the only way you can detect it is really to use some sort of a perturbation scheme and then keep on adding terms in the, say, for example, the linear elasticity is one special term in there. And you can do a second order effect as well. And solving the second order problem will give a better description of what is causing this. Which component in the formulation contributes to the difference. And that's the only way you can do this, yeah.
Okay, thank you. And maybe one more important question. I couldn't understand how many unknown variables or unknown functions are there in the final resulting system of partial differential equation. Do you formulate the system in terms of pressure or in terms of displacement or in terms of both pressure and displacement? I just couldn't.
For the simple cases, you formulate it in terms of displacement and pressure. Say, for example, the one-dimensional column test, the pressure is excluded. It comes out as a separate one.
Oh,
so in the case of, and that comes out as a separate one. So you only have the displacement in there. But in the case of the spherical and annulus one, you do get both coupled.
So my question is that if you use both variables or unknowns, pressure and displacement, then next question, do you use the same mesh for finite element mesh, for example, for these equations, filtration equation and elasticity equation, or do you use the same mesh?
In the finite element one, we don't make a distinction. You only make sure that the correct Galerkin formulation is there to get the pore fluid pressures at the midpoints of the elements correctly.
So excuse me, please. What kind of elements do you use? Trilinear or bilinear?
Just quadrilateral elements. Yeah.
Quadrilateral elements.
Yeah. You can use higher order elements as well, provided you make sure that the order of the displacements is higher than the order of the pressures.
Yes, right. Okay, thank you. Thank you. And I remember you said at the beginning of your presentation that there is a way to get to see your presentation. How it's possible to get it? I mean, can I get your presentation? Your talk? The text of your talk.
Yes, I can send the copies of the papers as well as the presentation to. Can I send it to Professor Kwasunto? Yeah.
Oh, so I can ask him for.
Yeah, well, whichever. If you send me your email address, I can send it to everybody.
Oh yes, I see. Thank you so much again. Thank you.
Okay.
We are recording your report now, and if you will allow, I can send this record of your report today. Everyone.
That would be wonderful. Yeah, I really appreciate that, and I'll be happy to answer any more questions if there are. Yeah. So.
Can I ask questions?
Okay. Professor Goriseva, nice to see you again. Yeah. Okay.
Nice to see you, and it's I'm very glad to be at this your lecture, and it's a wonderful lecture. Very interesting, important problems. I am involved in the problem of biomechanics, and also we consider the contact of the needle penetrating the brain tissue, and can try to now to develop a model for this problem. So
this
it was very interesting for me to hear you, to know more about modeling. And I'm interested, what is the influence of the structure, for example, of the size of the poral size in your model? What is the effect of poral size if we consider the brain, modeling of brain? And also, what is the limitations of the model related to the poral size? If there is a limitation.
I think if you are going to apply to real materials like the brain tissue, then you really need to get into some sort of evolving porosity. Because if you're doing indentation problems, for example, then the pore space will change, and that will change the fluid transport characteristics quite significantly. So you could use a porosity-based permeability, for example.
Porosity-based?
Permeability, yeah. So in other words, I think the problem can be best handled using computational techniques.
Only computation?
Yeah, I think
possible to use analytical or some simplification of the model to consider.
Yeah, I think it's possible, but there's so many iterations that you have to follow that it will be difficult to keep track of the progression, because the porosity, this is a time-dependent phenomenon. Okay. So that means that the pore fluid pressure front will be moving.
Yes.
And that will cause changes to the skeletal stresses with time. And to really follow the procedure where everything is evolving with time, it's difficult to do analytically. But computationally, it's the best.
I know, but I prefer the analytical method.
So do us.
Maybe I will talk with you later, maybe by mail.
So maybe some simple one-dimensional problems can be formulated using moving boundary techniques, for example. So it's something that I too am more partial to analytical techniques, but it sometimes it becomes unmanageable when you have the time variable involved, then it becomes quite unmanageable. So if you have plasticity as well as hyperelasticity and fluid flow, it does become a little more complicated than normal.
Okay, thank you. I understand, but maybe.
Okay.
Okay, thank you.
I think if there are any students that are working would like to contact me, but please feel free to let me know.
Thank you very much.
Okay.
Very interesting presentation. Thank you.
Okay, I want to conclude by thanking everybody for being there. It's a unique opportunity to do this for me, and then I regret that I couldn't do it in person. But I'm hoping that some future date we might be able to visit Lomonosov Moscow State University, and then meet everyone as well.
That we will. You're welcome in Moscow in our university, and we hope to show you everything. And
okay, Wonderful. Yeah. Okay. And thank you very much again. And please be safe.
Oh,
Yes.
thank you too.
Okay.
Be safe too.
Okay.
Yes, we will try to be.
Okay.
Thank you very much for very interesting presentation. We solved many problems in thermo hyper viscoelasticity when we solve some problems for Schlumberger company.
Okay. Yeah. Yeah.
Yes, and what can you tell about the correspondence between the numerical results and the results of some experimental studies?
Okay. This is definitely out of my area of expertise, but I'm very interested in making sure that people who do theoretical work or computational work also has some interest in making sure that the experimental results match. This is really it's extremely difficult to get good students who are also interested in doing all three aspects: the mathematical modeling, the computational modeling, and the experiments. I have had only about 2 students who can do this in my entire career, you know. So, but I think experiments are very important, and I try to emphasize the fact that one without the other is this tripod won't stand. You need the mathematical modeling and as one leg, the computational part with the other, and the experiments with the other. So this is really important to make sure that all three are on firm foundation as well. So in terms of the experiments, I think, you know, I try to do some experiments, not with hyperelastic materials, because that is a difficult issue. I can do this on fluid saturated hyperelastic material, not biological tissues, because it doesn't require clinical in vivo or in vitro testing. In the case of rocks, for example, it's much easier. Okay, so I can do the tests in my lab as well. But Schlumberger, they are also looking at wave propagation techniques. Whatever the theory that you have, you can derive results about the couplings and the individual properties using wave propagation techniques as well. So this is something that that I think needs to be explored fully. Most of the work that involves multiphasic media and wave propagation techniques will be extremely useful to look at both the static tests that are done, like indentation tests, for example, and then also look at wave propagation techniques, ultrasonics, etc. So there's room for a lot more research and interesting research as well. The more axes of research that you incorporate, then the easier it is to extend the theories more successfully, I think.
Thank you very much. Thank you.
Okay.
A little question from me. At the first part, you talked about one-dimensional model and specimen 1 meter length.
Right, yeah.
Is it only model, or you have experiments with biological
no,
media?
I think, you know, it's just purely as a model. I mean,
model.
just for the yeah. I didn't want to give the impression that it will.
1 meter brains.
Yeah, it's not a brain tissue. It's definitely not brain tissue.
Yes, okay. Yeah. Thank you. Thank you very much.
Okay, yeah.
I
So
will write the type. We are copying your lecture.
Okay. Okay. Thank you very much, and have a good evening. Yeah.
You too. Thank you very much, and take care.
Okay. You too. Yeah. Okay.
We are
Thank you for your lecture.
Okay. До свидания.
Thank you. Thank you.